Hi everybody. Well, today we've gathered here to actually study about the chain rule, that is differentiation of function of a function. So let me introduce you to this very beautiful article. How actually are we going to proceed ahead with its understanding, developing the result, how to apply it, connect it, memorize it, understand everything related to it. Now what actually is said by the chain rule? Chain rule stands to give you the idea of differentiation of a function of a function. What do you actually call function of a function process? That is called composition of functions, right? Okay. Obviously, this article deals with what? Individually, if you are given two functions which are differentiable, that means you pick up any point of their domain, their derivative exists there as a finite real quantity. If you have two individual functions which are differentiable and their composition is well defined, what can you say about the very differentiability of this composition function? What I'm trying to say is, if f and g are two differentiable functions individually given to you such that f o g exists, what can you say about differentiability of f o g is what we are going to study in here. Okay, so what does that result say, which is known very famously as the chain rule? It is the chain rule which gives you the very answer to this query, that if f and g are two differentiable functions, that what can you say about the differentiability of f o g, and if f o g is differentiable, how do you compute its very derivative at any point? That is given by the chain rule. So what actually does it say? Let's begin with the first part. There are two parts to it, and then you can actually extend it to as many parts as you want. Why am I saying that would be clear to you in a short while. Let's first talk about the first part. I'm saying let f and g be two differentiable functions. Let f and g be two differentiable functions, and f o g is defined, or f o g exists as a well-defined function. You know there is a condition based upon the existence of f o g. F o g exists only when range of g is contained in domain of f. It does not exist all the time. So this is important. F o g should exist for you to actually then talk about the differentiability of f o g. Let f and g be two differentiable functions and f o g is a well-defined function. Then the answer given by the chain rule is that f o g is also differentiable. Utter important conclusion. When two functions are differentiable and their composition is defined, then their composition is also a differentiable function. That's a beautiful conclusion. But the point is that if f o g is differentiable, that means you pick up any point from the domain of f o g, the derivative of f o g at that point is going to exist as a finite real quantity. How do you get that? The very chain rule itself says that, and the derivative of f o g at any point of its domain is computed in a very beautiful specific fashion. How? Please don't forget that this conclusion of f o g being differentiable is obtained based upon the hypothesis that fx is differentiable and gx is also differentiable. So of course their differentiability will be used in the very computation of derivative of f o g at a particular point. Fine. Derivative of f exists at each point of its domain, derivative of g exists at each point of its domain. So their derivatives are definitely going to be used in the computation of derivative of f o g at any point of its domain. What actually is the formula? It says that derivative of f o g at x is derivative of f o g at Which point? What do you think should be the answer? What actually we do is derivative of f of g at x, you know it is written as d by dx of f of g of x. Right? That's the another way of denoting the derivative of a function at a point. What you do is, in order to compute the derivative of f of g at x with respect to x, you first compute derivative of f of g at x with respect to gx. So first thing you understand, when I am talking about f of g, always I will be considering this f which is sitting as the first function as my former function. Once former function has been fixed, left out would be my latter function. So this function is left out, this is my latter function. F is my former function and this is my latter function. Fine, these are the two functions involved in the composition f of g. What I did? In order to compute the derivative of f of g of x with respect to x, I am first computing the derivative of composition function with respect to the latter function multiplied by the derivative of the latter function with respect to x. The independent variable involved is x. Okay, what we do is, in order to compute the derivative of f of g with respect to x, you compute the derivative of f of g with respect to the latter function g, multiply it by the derivative of that latter function with respect to the independent variable involved. Are you understanding it? This is the process which actually gives you the derivative of f of g at any point of its domain. And because this is existing finitely, finite quantity into finite quantity is obviously a finite quantity, and therefore we ensure that yes, derivative of f of g exists at each point of its domain. Why are they finite? Because g is given to be differentiable, f is given to be differentiable. Are you understanding? F of g of x is nothing but f of g of x. So here when I am talking about derivative of f of g of x with respect to g of x, I am using the very concept of f being a differentiable function, and therefore this derivative is a finite quantity. And here when I am writing derivative of g of x with respect to x, I am using the fact that g is a differentiable function, so this derivative is a finite quantity. Clearly finite into finite is finite, so this product completely is a finite real number. Now what happens is, rather than this, there is a very beautiful approach of understanding this particular fact about chain rule. Okay, when f and g are differentiable, then f of g is differentiable, cool. Another way of interpreting this chain rule is what? Try to understand this, it's very smart, precise, very beautiful. It says that, suppose z is a function of y. Suppose z is a function of y and y is a function of t. Okay? I am going to connect this with this. This is just another interpretation of the chain rule which is much more easier than this one. So let's try to understand this. It's not something new, it is just another interpretation of this. So I'll be making you connect this with this. So I have z is a function of y and y is a function of t. Stop. I am just trying to make a chain. Z is a function of y and y is a function of t. Stop. I am wishing to compute the differentiation of z with respect to t. See, if z is a function of y, I can very easily compute differentiation of z with respect to y. If y is a function of t, I can very easily compute derivative of y with respect to t. But z directly is not a function of t, and therefore how to compute the derivative of z with respect to t? Derivative of z with respect to t is given by derivative of z with respect to y, which I just told you is easy to compute because z itself is a function of y, multiply it by derivative of y with respect to t, which is again easy to compute because y itself is a function of t. When you multiply these two, you get derivative of z with respect to t. This is how the chain rule works. Okay? How is this another interpretation of this result? I am saying z is a function of y is a function of t, you want derivative of z with respect to t. Here what is happening? You have fog of x, right? What are you doing? I am saying derivative of fog with respect to x. Please see. My fog is playing the role of z. Fine, fog is playing the role of z. This can be written as f of g of x, right? F of g of x. So I can say, if I take this gx as suppose y, if I take this gx as y, I can say z is function of y, isn't it? Z is equals to f of y, gx is y. Fine. I can say z is a function of y and y is a function of x. So z is a function of y is a function of x. Exact same picture. I'm just trying to connect this result with this result. Z is a function of y, where y is g of x I have taken. That means y is a function of x. I am interested in computing derivative of z with respect to x. Z is my fog only, please understand. So derivative of z with respect to x is derivative of fog with respect to x. This is given by derivative of z with respect to y. Derivative of z with respect to y. Y is what? Gx. Z is what? fog. So derivative of z with respect to y multiplied by derivative of y with respect to x. Y is what? With respect to x. Isn't this the exact same thing that's written over here? Right? So this is another way to interpret this same result, which is my chain rule corresponding to differentiation of composition of exactly two functions. What about the extension? Before I move to the extension, let's just try to apply this. Let's try to apply this chain rule. Okay. In here, when I'm talking about the application, let me consider this question. It says compute the derivative of sine of x square plus 1. That's the function given to me, and I am being asked to compute its very derivative. Clearly, until and unless you are able to decode that the given function whose derivative you wish to find is the composition of two already differentiable functions, you cannot connect this to the chain rule and hence cannot apply the chain rule, whether in this form or in this form. So the first very thing is you should be very smart in decoding that the given underlying function is actually composition of already two differentiable functions. Now see, I can say sine of x square plus 1 is a composition of, it's clearly a composition of sine x function and this polynomial function x square plus 1. Individually, if I talk about sine x, we have already proved in our previous lectures that this is a differentiable function, right? It's a throughout differentiable function. And any polynomial function is also throughout differentiable. That means it is differentiable on its entire domain, which is my collection of all real numbers. So even this is a differentiable function. Individually, if both the functions are differentiable, one conclusion is completely established. This implies that sine of x square plus 1 is a differentiable function. First conclusion. Until and unless my function is not differentiable, how can you even talk about computing its derivative at a certain point of its domain? So here we have established that sine of x square plus 1 is a differentiable function. Now I can talk about computation of its derivative at a certain point of its domain. Fine. So if I pick up x as any point sitting in the domain of sine of x square plus 1, I will be getting or interested in getting the derivative of this function at that x. That x is arbitrarily chosen, and therefore I would be getting a formula to completely obtain the derivative of this function at any point of its domain. Cool? If these two strategies, which actually is one single strategy only, just written in two different formats, is clear to you, I'm going to rub this, and here we're going to actually compute for this very question the derivative. Okay, this is what we have. Now I'm going to adopt two strategies to compute the derivative. Method 1. See, I can say f of x is sine of x square plus 1, which can be written as GOH of x, where h of x is x square plus 1 and g of x is sine x. So if hx is x square plus 1, gx is sine x, then GOH of x is g of x square plus 1, which is sine of x square plus 1, which is f of x. And therefore, GOH is completely well defined. F is my function which is written as composition of two functions. F is a function written as composition of two differentiable functions. How to compute? My aim is to compute derivative of f with respect to x, that is derivative of GOH of x with respect to x, and here we have already ensured that g and h individually are differentiable functions. So yes, GOH is differentiable, and hence our very journey of computing its derivative is a valid journey that we are beginning to undertake. Now, how to get this? Two ways are there. We are on method 1. What you do? G is my former function, h is my latter function in here. So, d by dx of GOH of x will be derivative of GOH of x with respect to the latter function multiplied by differentiation of the latter function with respect to the independent variable involved. What is this? Just plug in. GOH is nothing but f, which is sine of x square plus 1 upon d hx. Hx is nothing but x square plus 1 multiplied by d by dx of h of x, which is again x square plus 1. Now this is something very, very nice. This is what makes this very easy. How? If you take x square plus 1 to be equal to u, suppose you take that, let x square plus 1 be equal to u. Then the process becomes utter simple. D by dx of GOH of x is equal to d by du of sine u multiplied by d by dx of x square plus 1. Aren't these utter easy differentiations? D by du of sine u is cos u. D by dx of x square plus 1 is d by dx of x square plus d by dx of 1. D by dx of x square is 2x plus d by dx of 1. The differentiation of a constant function is 0. So 2x plus 0 is just 2x. You have 2x into cos u. But obviously the differentiation of a function of x is again a function of x. So replace u by what it is in terms of x. So u is x square plus 1, 2x cos of x square plus 1. Understood? This is one way of obtaining the differentiation of a function written as composition of two functions. So that's done. This is nothing but d by dx of f of x. I am applying chain rule over here because f is written as composition of two already differentiable functions. Now another way of computing this is what? Another way in which you can compute. Now it's not actually another way. I would say it's the same way but written in a more simplified format. Fine? So let's talk about this method 2, which was just another interpretation of the chain rule that we had first written. Now, in here, I would be not talking about all of this. I am saying fx is sine of x square plus 1. See, I'm saying let x square plus 1 be equal to t. Fine. Here this is what? X square plus 1 is t. Suppose I'm taking this as h of x. Fine. This implies t is a function of x. Cool enough? Therefore, f of x is equal to sine t. This means f is a function of t. So I have what? F is a function of t and t is a function of x. Try to get the chain, the league, the connection. F is a function of t, t is a function of x. Computing derivative of f with respect to t, beautiful. Computing derivative of t with respect to x, beautiful. What about computing derivative of f with respect to x? It requires going through this chain of derivative of f with respect to t and derivative of t with respect to x. You cannot directly compute derivative of f with respect to x. You will have to follow a chain, a league, a process. You have to compute derivative of f with respect to t because f is a function of t. Then also compute derivative of t with respect to x because t is a function of x. That's how you are going to get the connection between f and x and hence get the derivative of f with respect to x. And therefore, derivative of f with respect to x is derivative of f with respect to t into derivative of t with respect to x. That is d by dt of sine t multiplied by d by dx of t is x square plus 1. We have obviously landed ourselves to the exact same step like we had in our method 1. Just in place of t there was u written, nothing else was different. D by dt of sine t is again cos t. This is again just 2x. Fine. Differentiation of f with respect to x will be a function in terms of x only. So I will be replacing t by what it actually is. It is x square plus 1. So you have the exact same answer. Clear? So the very first step is to actually be able to decode that the given function is a composition of two functions and then apply a chain rule to compute its derivative. Now, if I talk about the next situation, let's see if we can, just by the understanding of chain rule for composition of two functions, are we able to actually understand the extension of this chain rule for composition of three functions and deduce the conclusion by ourselves only. So let's begin this discussion. I am saying f, g and h are differentiable functions. We are going to develop both the mechanisms to compute the derivative of their composition. Okay? This implies f, o, g, o, h is also differentiable. First conclusion, composition of any number of finitely many differentiable functions is differentiable actually. So even if there are 4 differentiable functions, their composition is again differentiable. If there are 5 differentiable functions, their composition is always again going to be differentiable. So composition of differentiable functions is always going to be differentiable. How is the very method of computing the derivative of this function going to be followed now? So see, this is also differentiable function. So I can now talk about the existence of its derivative at a point. I am saying I am interested in computing the derivative of f(o)(g)(o)(h) of x with respect to x. Try to recall what was the derivative of f(o)(g) with respect to x. Derivative of this complete function with respect to the latter function multiplied by derivative of the latter function with respect to the independent variable. Derivative of this complete function with respect to the latter function. If I take f as my former function, complete g(o)(h) is my latter function. So with respect to the latter function multiplied by differentiation of latter function with what? Right now you cannot say with respect to the independent variable x. Right now it is composition of two functions. So right now if I only focus upon this, g is former, h is latter. So derivative of g(o)(h) with respect to latter multiplied by derivative of this function, which is sole single function with respect to x. That's how this gets extended from 2 to 3. This is the chain rule for composition of 3 differentiable functions. And over here, if I try to move towards the next interpretation of this chain rule, what would that be? Here the thing is, if z is a function of y and y is a function of t and t is a function of u, isn't that the situation? That is the same situation if I am talking about f(o)g(o)h) of x. This is f of g of h of x. Suppose I am taking this to be equal to y. Fine. I am interested in dy by dx. So see, if I take hx as t, I have y as f of g of t. Then if I take g of t as u, I have y as f of u. So what is it that I have? Y is a function of u, where u is a function of t, where t is a function of x. Isn't that amazing? I have y is a function of u is a function of t, and t is a function of x. I am interested in computing derivative of y with respect to x. How would you do that? How would you do that? Just follow the chain. I am interested in computing derivative of y with respect to x. What would you do? The thing that you did in the case of 2. Derivative of y with respect to u multiplied by derivative of u with respect to t multiplied by derivative of t with respect to x. That's why it's called a chain rule. Similar thing I was writing over here in just some other symbols. If z is a function of y, y is a function of t, t is a function of u, and you are interested in computing derivative of z with respect to u, then derivative of z with respect to u would be what? Derivative of z with respect to u will have to actually be computed by following a certain chain. Compute derivative of z with respect to y, then multiply it with derivative of y with respect to t, multiply it with derivative of t with respect to u. And here I just showed you that this is not something foreign, it is actually connected with this only in a different interpretation. And that's what I wanted to show you from here. Pick up this question. Pick up this question and try to compute its derivative with the help of chain rule for composition of 3 functions. It's sine of cos of x square. And we'll be discussing it in the next lecture. So your next lecture is going to start right after 20 minutes. Right now it is 1:30. So next lecture is going to be from, you can just assume it's 1:45 to 1:50. In 15 to 20 minutes will be the next lecture beginning. So that's it from my side, guys. Don't forget to do this question. Just apply your chain rule. In fact, I would give you one more homework. Try to develop chain rule for composition of 4 functions in both the formats. Okay? That would be super interesting. So that's it from my side. Thank you.